Molecules are incredibly small, but are there more sand grains on Earth than atoms in a single raindrop? At first, this sounds like that can't be true, right? Like there are a lot of grains of sand if we count every desert, every beach on the entire planet. So, let's think about this problem for a minute. There are an estimated 7.5 times 10 to the 18th grains of sand in the world. That is an unfathomably big number. I'll admit, I have no way to process that number. I can tell you what it is and I can do math on it, but in my head I can't imagine what would 7.5 times 10 to the 18th donuts look like? I have no idea. I'm pretty sure that's enough donuts to flood the entire planet and create a layer of donuts around the Earth. So for things we think of in our heads, this number is really big. And if you were to tell me another really big number, well, I can mathematically tell you one's bigger than the other. I can't really think of them. So it's hard to work with. So what I do know, though, is that it's got to be a whole lot. Now, let's take a single drop of rain. So a drop of rain has a volume of approximately 0.034 milliliters and a density of about 1 gram per milliliter. We're going to say that 18.02 grams of water contains about 6.022 times 10 to the 23rd molecules of water. Note that in this chapter, we're going to learn where that number comes from. So I promise I'm not just going to leave you with, well, of course you should know this. But we'll get to the point where you'll know this, and you can actually calculate how many grams of water, how to get from grams of water to molecules of water. By the end of this chapter, you'll be able to do it just like I am here. But for now, I'm just going to tell you, this is the conversion between grams of water and molecules. So let's solve this question. So first, we're given this information. We have an estimate for the grains of sand. We've got a drop of water and what its volume and density is. And we know that what a mass of water, how we convert it to molecules. And then one last fact that wasn't mentioned directly in the question would be something you might have to think about if you were solving this problem yourself, is that 1 molecule of water contains exactly 3 atoms. Also note that we have not yet taught you that, but this is something by the end of this chapter you would have an idea for, a molecule has 3 atoms. Gotcha. A molecule of water. Not all molecules have 3 atoms, but water specifically does. So let's try solving this question with this information. So we want to start with our drop of water, and we want to get it to something we can compare to our grain of sand. So we need to know for our drop of water that has this volume, we need to know how many molecules of water are in that. So we're going to start with our 0.034 milliliters. And I may not be 100% sure where to go from here, but I know that the only thing I have that can convert milliliters to anything is this right here, my density. I know that 1 gram of water has a volume of 1 milliliter. So I know for my 1 milliliter, I get 1 gram of water. I then know right here, while it's in words, that's the same thing as saying 18.02 grams, and that should be an 8, is equal to 6.022 times 10 to the 23rd molecules of water. So if I have 18.02 grams, I could use that to convert to 6.022 times 10 to the 23rd molecules. And then finally, we know that 1 molecule of water contains exactly 3 atoms. So now, let's plug these things in. We have 0.034 milliliters, and we're going to multiply it by our number of atoms, our number of molecules per gram. We'll divide it by 18.02, and then there are 3 atoms in every molecule. Make sure I put all my math in right. 0.034. Is that right? Yep. I'm trying to make sure I don't make any more mistakes after what I did in the last chapter. Times that number divided by 81. Yep. So from that, we're going to get that we have and there are 2 sig figs. So 3.4 times 10 to the 21st atoms in 1 raindrop. So if you look at that, what you'll notice is this number is greater, 3.4 times 10 to the 21st is greater than our grains of sand, which was 7.5 times 10 to the 18th. So this is indeed larger. There are more atoms in a drop of water, a single raindrop, than there are grains of sand on the entire planet of Earth. This is to give you an idea that when we are working and talking about how many molecules are in something, the numbers we're working with are absurdly large. Now, we will be using different terminology. We're going to learn about something called the mole in this chapter so that we can work with numbers you actually understand. We're not going to solve problems where we say, I've got 4.9 times 10 to the 23rd molecules of hydrochloric acid. Is this enough to do my reaction? We're not going to do that because those numbers become so big we can't work with them very well. So we'll learn a new unit in this chapter that will help us work with these giant numbers and turn them into numbers our brains can think about. So instead of using giant numbers, we're like, oh, that's half a mole, instead of some giant number that doesn't mean a whole lot. But I want you, because when we work with those new units, sometimes people forget how big that unit really is. So that's why I like this question. When we're talking about atoms, we're very, very small. There are more atoms in a drop of water than grains of sand on the entire planet. And it's not just a little bit more. That's a factor of, you change 10 to the 21st compared to the 10 to the 18th, means that you're changing by 3 digits. It's like 1,000 times. Now, the front numbers are different, so it's like 500 times as much as an approximation. But that's absurdly large. And I just want you to help remember that when we're working on problems. Also, as a side note, remember that this is indeed larger than this, even though 3.4 is not as big as 7.5, because you need to go to your number up here first, our exponent, because 10 to the 21st is definitely bigger than 10 to the 18th. It would only be if they were the same exponent that then we would have to compare the numbers up front, as long as they're both in scientific notation. So now, we got to introduce a few conceptual things related to matter so we can talk about some more stuff. So we need to know, how did I get from 18.02 grams of water to 6.022 times 10 to the 23rd molecules? Let's talk about what matter really is and what molecules are and such. So a little bit of this may be some review, but we're going to go over it so we make sure we're all on the same page. And some of these things may be things you know, but I may use the terminology a little bit differently. So I want to make sure we're in agreement there. So please, that's why we're going through some of this, even though you have probably heard solid, liquid, or gas a couple of times in school before. But these are the definitions we're going to work with. So we're going to primarily work with 3 states of matter in this class: solids, liquids, and gases. If you know of other states, they do exist. You are right. These are the 3 we're going to work with in general chemistry, though. Mostly. We'll have a 4th one in the 2nd semester, but we'll explain it when we get there. So solids have atoms or molecules that are packed very close together, and because of this have a fixed volume and rigid shape. So I'm going to use water for all 3 examples. So if you have an ice cube, assuming it's frozen and it's not melting, because once it's melting it's becoming a liquid, but when it's frozen, it's got a really set shape. I'm not going to take an ice cube and go up to a pitcher and put it in and expect it to change shape. Like, oh, the ice turned into a circular shape because I put it in a pitcher. So let's say I've got my pitcher and I add some ice cubes, they're going to stay like this. And okay, these are giant ice cubes or the world's tiniest pitcher. Let's pretend it's like a coffee cup I wanted to cool down. Something like that. So if I put these ice cubes in, okay, they wouldn't be floating either. I'm bad at drawing. But they're going to stay solids. They're going to stay ice. They're not going to do anything different there. On the other hand, so this is my solid state. On the other hand, if I were to just pour some hot water in that was a liquid, so I'm pouring it in, it's not going to stay the same shape though. Like if I've got a jug of water, it's not going to stay the shape of the jug. Instead, it's going to take the shape of the cup. But it's also not going to change volumes. It's going to stay the same volume. So for this reason, we say liquids have atoms or molecules that are packed close together, but are able to move some. So they have a fixed volume, but not a fixed shape. So I'm not going to get suddenly a higher volume of water when I pour it into a new container, but it will change its shape to match that container. Now gases have atoms or molecules with lots of space between them. And because of this, they have neither a fixed volume or shape. So if I try to put some steam in my cup, it's just going to be all around, and we're not going to see it because it's going to be in a gas form and it's going to be colorless. And if I don't have a top to the cup, it's going to come out of the cup as well and spread out. I'm not going to be able to confine that steam into the cup because it doesn't have a high enough density to do that. So you could make some gases that would stay in there, but they're still going to be spread out a lot, and they're not going to have a set volume. So my gas isn't going to stay in whatever shape it was before. It's going to move around and fill up the whole room that cup is in. The water's going to spread out. So now, sorry, I didn't mean to go back. So now let's talk about the composition of matter. So how are we going to distinguish different types of matter from each other? So we have 2 main types. First, we have pure substances. What this means is whatever we're working with is only made out of one type of particle, whereas a mixture is going to be made out of multiple types of particles. So going back to our water example, a cup of water is a pure substance. So, cup of water, equals pure. On the other hand, if I take the same cup of water and I add, let's say, some lemon juice and some sugar, because I don't want plain water, I want lemonade, well, now we're going to have a mixture. Because it's not just water. There are lemon juice particles and there are sugar particles spread throughout. So now lemonade is going to be a mixture of lemon juice, sugar, and water, whereas my cup of pure water is going to be a pure substance. We can even break these down more too, though. So pure substances can be classified into two categories. Elements, you can't break those down any further, whereas compounds are going to be broken down into simpler substances. So for example, if I have a helium balloon, helium is an atom. It's one type of atom, so we're not going to get anything else inside my balloon. I can't take helium and break it apart into simpler substances. But other things will be broken down. So table salt's an example, but also my cup of water. Water, if I were to, for example, use electricity to do something called electrolysis, I could break apart the water into hydrogen and oxygen. Now those hydrogen and oxygen elements would be elements because they're going to be on their own and they're not going to have different things connected to them. We can't make them simpler. My water can be broken down. So as we discuss atoms and molecules, I think that example will also make more sense as we'll start to learn that elements are only going to have one type of atom in them, which is what everything else is made out of. So compounds have multiple types of atoms combined together. And then finally we have mixtures. So like my lemonade, I can also define that. We have some that are homogeneous. So my lemonade example would be a homogeneous mixture. On the other hand, if you're at a beach and you have some wet sand where the bottom of it is basically all sand, and then up top, it's mostly water. But then down here in the middle, you have some mixtures where sometimes it's got some sand and some water. So in different parts of it, there's going to be different amounts of water particles compared to sand particles. Whereas in my lemonade, it should be the same throughout. If I take the top of the lemonade and compare it to the bottom of the lemonade, it's going to have similar amounts of lemon juice, sugar, and water. So homogeneous means it's going to be the same throughout. Our heterogeneous mixtures, though, are going to be different in different places. I can clearly point out this part of the mixture has a different different makeup than another part of the mixture. So these are just some basic definitions of how the composition of matter and phase of matter that are important for us to be able to talk about atoms in this section and matter.